So if you're into robotics, you have definitely seen those jaw-dropping new videos of Figure 03. I mean, it's walking, it's carrying boxes, and it's squatting. And not just any squat, but a deep, fluid, human-like squat that honestly has been a huge roadblock for humanoid robots until now. So what's the secret? Well, let me tell you, it's not just some fancy new software. Nope. This is a real, fundamental breakthrough in the mechanics of the robot itself. We're going to dive deep into the patent that looks like it's finally cracked the code for humanoid mobility.
And this right here, this is the key to all that incredible agility. See, it all comes down to solving one incredibly frustrating problem. A problem that's been a thorn in the side of roboticists for decades. We're talking about a glitch that can literally lock a robot solid, making it totally useless for the simple, everyday tasks we need them for.
All right, so let's get into the big obstacle. I mean, why is something as simple as a squat, something we do without even thinking, been so ridiculously hard for these super advanced machines? Well, the answer is this nasty little engineering trap hidden deep inside the robot's hip.
Okay, so the technical term is kinematic singularity, but you can just think of it as gimbal lock. And here's a great way to picture it. Imagine one of those gyroscopes, right? When its rings all line up perfectly, boom, it just freezes. It can't rotate anymore. Well, the exact same thing happens in a robot's hip. The axes of rotation line up, and suddenly the robot loses a whole degree of freedom. It can't be controlled. It's stuck. For a robot, this is a catastrophic failure, and it has been a massive headache for pretty much every conventional design out there.
And what's really fascinating is the kind of design trap this whole problem created. For years, the thinking was, hey, if we want more motion, we just need to add more motors, more actuators. Those are the robot's muscles. But that approach just backfired. It made the robots heavier, way more complex, and they burned through battery life like crazy. And the worst part, it actually made the gimbal lock problem even worse. It was a total dead end. So Figure AI did something different. Instead of just throwing more parts at the problem, they went back to the drawing board and completely rethought the geometry. They chose a smarter, much more elegant design.
So the big question is, how did they pull it off? Well, the patent lays out this beautiful three-part solution that just elegantly sidesteps the entire problem. So let's get into the engineering secrets that make this robot move in a way we've never seen before. All right, here they are, the three core breakthroughs. You've got non-orthogonal axes, no torso pitch actuator, and a hyperboloid pelvis frame. Now I know, they sound a little technical, but trust me, each one is a really clever piece of a much bigger puzzle. We're going to break them down one by one, and we'll start with the crazy geometry of the hip itself. Okay, check out this drawing from the pattern. This reveals the first big secret. You see, most robot hips are built with perfect 90-degree angles. It just seems logical, right? But Figure's design, it intentionally throws that out the window. They offset the hip's roll axis by about 15 to 25 degrees. It's such a simple little geometric trick, but the result is huge. It means the axes can physically never align perfectly while the robot is operating. Just like that, gimbal lock goes from a constant threat to a physical impossibility.
There's an analogy for this that I just love, because it makes the whole concept click instantly. It's like one of those wooden artist mannequins. Think about it. Those things are designed specifically to hold all sorts of fluid, natural poses, and their joints never lock up. And how do they do it? With angled pivots, not stiff 90-degree angles. It's just a simple, super robust, and frankly, brilliant solution.
All right, on to the second breakthrough. And this one is completely counterintuitive. You're going to love it. To make the robot bend forward better, what did Figure AI do? They got rid of the motor that bends it forward. I'm not kidding. There is no dedicated motor, no actuator in the robot's belly to make it bend at the waist. So, how in the world does it bend over? Simple. It just uses the massively powerful actuators in the hips, the exact same ones that move its legs to pull the entire upper body forward. This is a genius move called functional consolidation. Basically, you're making one set of parts do two jobs. It puts all the heavy lifting stress on the strongest motors in the whole system, and you get to remove a bunch of parts. That means less weight, less complexity, and fewer things that can break. It's a huge win.
And that brings us to the third innovation, and this is the piece that really ties it all together, the pelvis. Now, this is not just some flat metal plate. The patent calls it a depth-elongated lateral hyperboloid, which is a mouthful, I know. But basically, just picture a strong, curved 3D frame.
A much better way to think about it is less like a flat sheet of metal and more like the arch of a bridge. It's a shape that's engineered for incredible strength with the absolute minimum amount of material. And here's why that specific shape is so crucial. First, that 3D curved structure gives them the perfect angled surfaces to mount those weirdly angled actuators we talked about. It also just naturally creates a ton of room inside for all the wiring and other components. And maybe most importantly, it distributes all the forces and stresses way more efficiently, making it both stronger and lighter. It's really the keystone that locks the whole design together and makes it all work. Okay, so let's recap. We've got our 3 core ideas: angled axes, no belly motor, and that cool curved pelvis. Now, let's take a look at how all these pieces actually come together in the final assembly.
I love this exploded view from the patent. It just shows everything so clearly. Right up top, you've got the waist. Then in the middle, there's that unique hyperbolic pelvis frame. And then you can see how the hip actuators for each leg are all integrated into this one super compact unit. There's just no wasted space, no clunky brackets. It's just clean, elegant, efficient design.
Okay, now let's go even deeper inside the machine. This cross-section shows us the actuators, those powerful electric muscles, all packed tightly inside the hip. You can literally see how the motor for bending the leg forward is nestled right up against the motor for rolling the hip from side to side, and it's all arranged at that crucial non-90-degree angle. It's just an incredibly dense and efficient way to package all that power and motion.
So, okay, the engineering is obviously brilliant, but let's get down to brass tacks. For an investor, what does all this clever design actually mean? What's the real competitive payoff here? Well, let's just start with the raw performance numbers. This design unlocks a massive 200 degrees of hip flexion. Now, to put that in perspective for you, that's actually more range of motion than the average human hip. And that number, that's the key. That's what lets the robot go from standing perfectly straight all the way down into a full deep squat. That's a capability that is absolutely non-negotiable if you want a robot to work in our world.
And it's not just about the legs either. The waist assembly gives it 170 degrees of torso twist. So what does that mean in the real world? It means the robot can grab something off a shelf to its side or even behind it without ever having to move its feet. In a place like a warehouse or a factory where every single second counts, eliminating those extra steps is a massive gain in efficiency. It saves time and it saves energy.
And really, this is the bottom line. What we're looking at here isn't just some small incremental improvement. This is a genuine strategic advantage. You're eliminating a catastrophic failure mode right from the start. You're reducing the total number of parts, which automatically lowers your manufacturing costs and makes the whole thing more reliable. And it's more power efficient, which means longer runtimes on a single charge. So from a pure design and investment standpoint, what you have is a system that is more robust, more scalable, and ultimately a whole lot more commercially viable.
So what this all really boils down to is this. By going back to square one and rethinking the robot hip, Figure AI didn't just teach a robot how to squat. They've created a foundational piece of intellectual property that solves a core problem that has held this entire industry back for years. And that, well, that leaves us with the billion-dollar question, doesn't it? Is this clever combination of geometry and consolidation the elegant solution that finally unlocks the door to commercially viable general-purpose humanoid robots at scale? You know, only time will tell for sure, but the blueprint we're seeing here looks very, very promising.